Hello, my name is Desmond Edagisi, and I'm here to take us on the subject mathematics. Today we'll be looking at the theme numbers and numeration. And under numbers and numeration, we'll be learning about sets. And our topic under sets is relations between sets. Let's go into our class to find out more. In the course of our class, we're going to learn that there are certain relationships or interactions that take place between given sets. And one of such relationships brings about a concept we know as equality. Also, we'll study about what disjoint sets are all about. We'll also find out about the concepts of equivalence that occurs between sets. Next, we'll find out all about subsets. Then, we'll learn about power sets. It promises to be an exciting class, and I know you're looking forward to it. Let's go into our class. Two sets, say sets A and sets B, are said to be equal if and only if they have exactly the same elements. And to illustrate that relationship, we simply say set A is equal to set B. Now, there are certain facts that we need to know about equality. One of that is the order of the elements listed does not really matter. Let's take, for instance, if we are given a set A as a set that has elements 1, 2, and 3, while our set B has as its elements 3, 2, and 1. Notice that the same elements that are in A are all present in B, but they are arranged in a different manner. We say that the order of the arrangement does not matter as long as the sets are the same. Next, we say that repeated elements in a set are basically ignored. Let's take, for instance, again, we have a set A with its listed elements as 1, 3, and 5. While we have set B with its listed elements as 1, 5, 5, 3, 1, and 3. Notice that there is a repetition. 5 is repeated twice, while 3 is also repeated twice. We say that the repeated numbers are counted as 1, and therefore we simply say also that our set A here, which has all of its elements all present in B, is equal to B. Let's go on to learn some more. Again, let's take this graphical illustration here. If we have our set A has as its elements 1, 2, and 3. While set B has as its elements 3, 2, and 1. Like we said earlier, notice our set has 1 present in B, 2 is also present in B, 3 is also present, but B is arranged backward. We say that as long as all elements in A are present in B, the order in which either of the elements are arranged does not matter. So again, A is equal to B. Let's go on and take some examples. If we have a set A with elements R, Y, U, and D, while we have a set B with elements A, T, N, and U, if set C also is a set that has elements C, A, U, T, and A, and set D has elements Y, R, Y, D, U, state if the following is true or false. So let's determine if A is equal to B and if A is equal to D. To do that, we'll quickly take a look at the elements of every one of our sets here. Let's quickly take a look at A again. A has elements R, Y, U, D, while B has A, T, N, U. Notice that our U is present. That's the only element that is present in each of our given sets. It simply means that every other element is different from one another. Therefore, we say that A is not equal to B. For A to be equal to B, we said all the elements within A must be present in B. So A is definitely not equal to B. Let's again take a look at our set A. Set A has elements R, Y, U, and D, while D has elements Y, R, Y, D, U. Notice the repetition. Again, we said repeated cases are ignored. So we have Y, R, D, and U. And if you notice, A also has R, Y, D, and U. It therefore means that all the elements in A are also present in our set D. Therefore, A is equal to D. This is absolutely correct. Let's take a look at another example. If we were given a set J has elements D, C, A, and B. Which of the following sets are equal to J? Again, we said for two sets to be equal, every element must be present in each set. So we have a set N that has elements C, D, E, B, and A. If we compare our set N with the set J, we'll notice that our set J that has element D is also present in our set N. Element C in our set J is also present in our set N. A is also present, B is also present, but E that is present in N is not present in J. Therefore, we say J is not equal to N. Let's take a look at our second statement here. T is equal to the first four letters of the alphabet. We need to confirm if this set T is equal to J. Again, we compare the elements of our set. If we list out the elements of the set T, we'll have A, B, C, D, which are the first four letters of the alphabet. Again, if we compare the first four letters of the alphabet with our set J that has D, C, A, B, we'll find out that every element in our set T is also present in J. Therefore, we say T is definitely equal to J. Let's go on to learn some more. Whenever we have a situation where two sets have no element at all in common, we say such sets are disjoint sets. For example, our set here has its elements 2, 3, 4, 5, and 7, while our other set has elements 9, 11, 13, 15, and 71. We notice that there are no similarities at all between both sets. Such sets are said to be what? Disjoint sets. Let's take a look at another relationship that exists between our sets. The concept of overlapping is an occurrence that happens when two sets have only some elements in common. That is, some of the elements present in one of our sets can be found in the set that has other elements. For example, again, if we have a set here that has as its elements 3, 4, 6, 7, 8, 9, and 11, while we have another set that has elements 3, 5, 7, 9, 12, 13, and 15. If we did a quick comparison, we'll find out that 3 here is present in both sets. We also have 7 present in both sets. We have 9 present also in both sets. We say such sets are overlapping because they have some of their elements in common. Let's go on and take some examples. If we were asked to confirm if these two sets are disjoint, let's see if we can do that. M is a set that has elements R, E, L, and A, while D is a set that has elements C, I, O, M. We find out that all the elements of our set M cannot be found in the elements of our set D. It therefore means that M and D, which are our given sets, are disjoint. So this is true that our sets are disjoint since they have no element at all in common. Let's take a look at another example. We are asked which of these sets are overlapping. So we have our set A with its elements listed as 2, 3, 5, 6, 9, 14, and 22. Our set B has elements 1, 7, 3, 11, and 15. Our set C has elements 2, 4, 6, 8, 10, 12, 14, up to 22. Let's confirm if any of our given sets overlap. So we do a quick comparison of the elements of our sets, and we find that all our given elements in set A cannot be found in set B. So we can quickly say that A does not overlap with set B. If we also compare the elements of our set A and our set C, we'll notice that the element 2 found in set A is also found in set C. The element 6 found in set A is also found in set C. The element 14 found in set A is also found in C. And the element 22 found in A is also found in C. So we have 4 elements in common between our set A and our set C. Of course, such occurrence leads us to say that A overlaps with C. Another relationship that exists between sets is one of equivalence. 2 finite sets are equivalent if they both have the same number of elements. So if you have a given set A, for instance, that has elements 1, 2, and 3, while our set B has elements P, Q, and R. The cardinality of our set A, which would be a count of the unique elements within our set A, would give us 3. The cardinality also of our set B, which is the count of the number of elements in set B, would also give us 3. It therefore means that A is equivalent to B. A quick fact for us to know is that all equal sets are equivalent. Remember, we said equal sets are sets that have the exact same elements within each set. So if A is equivalent to B, it means that if there are 5 elements in A, and they are, for instance, the numbers 1, 2, 3, 4, and 5, there would also be 5 elements in B with the same elements 1, 2, 3, 4, and 5. Such sets are equal. If we did a count of the number of elements between sets A and B, we have 5 elements in set A and 5 elements in set B. Therefore, these 2 sets, which are equal, are also equivalent. But note that all equivalent sets are not necessarily equal. The example we gave earlier on confirms this fact. If we did a count of the elements of our set A, we'll have 3 as our cardinality. And if we did a count of the elements of our set B, we also have 3. But note that the elements of each set were completely different. The elements of set A were numbers, while the elements of set B were all letters. So again, all equivalent sets are not necessarily equal. Let's take some examples to buttress our fact. If A is the set that has elements R, Y, U, and D, and B is the set that has elements A, T, N, and U, C is the set that has elements P, M, V, X, S, and E, while D is the set that has elements Z, G, T, O, and Y. Which of these sets are equivalent? To check which of our sets are equivalent, we'll have to do a count of the elements of each set. The cardinality of element A, which is a count of the unique elements within our set A, is 4. The cardinality of our set B is also 4. The cardinality of our set C, which is a count of the number of unique elements within our set C, is 6, while the cardinality of our set D is 5. So again, if we notice, our set A and our set B have the same number of elements within their sets. So A therefore is said to be equivalent to B. Let's take this other example. If G is the set of whole numbers between 3 and 13, A is the set of alphabets A to I, if Z is the set of all X such that X is in the range between 13 and 1, which of these sets are equivalent? Again, let's list out all our sets. The set G has the set of elements that are whole numbers between 3 and 13. The word between tells us that the range of our numbers would not have 3 and 13 as its boundaries. So we would have our list as 4, 5, 6, 7, 8, 9, 10, 11, and 12. Let's also list out the elements of our set A, and that would give us alphabet A to I, A, B, C, D, E, F, G, H, I. Next, let's list out the elements of our set Z, and this would give us 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So quickly, we do a count of the number of elements in each of our given sets. The cardinality of G, which is the count of the unique elements within our set G, is 1, 2, 3, 4, 5, 6, 7, 8, 9. The cardinality of our set A is 1, 2, 3, 4, 5, 6, 7, 8, 9. And the cardinality of our set Z is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we notice, our set G and our set A have equal number of elements in their sets. Therefore, we say G is equivalent to A. One major concept that exists as a result of interaction between sets is the concept of the subset. A set, for instance A, is called the subset of B if every element of A is also an element of B. To illustrate that relationship, there is a symbol that we make use of. So that symbol is written in this manner. Therefore, this statement reads that A is the subset of B. We could also say that A is contained in B. Our symbol can also be written in a reverse manner, which also reverses our statement up here, and the symbol symbolizes a superset. A superset implies, for instance, that B contains A, or B is the superset of A. Also, if A, for instance, is not the subset of B, we write our symbol and we negate that symbol by drawing a slash across it to say A is not a subset of B. Let's take a practical example to better understand the concept of the subset. Here we have a set of mathematical instruments. We have our ruler, we have our protractor, and we have our set square. If a student were to select any of our equipment here and to select it in a number of manner, take for instance, he selects 1 at a time, or he selects 2 at a time, or he selects 3 at a time. Let's take a range of all the possible ways he could make his selection. He could select 1 at a time, like we said, select just a ruler, or just a set square, or just a protractor. He could also select 2 instruments at a time. Maybe he selects the ruler and the set square, or he selects the ruler and the protractor, or better yet, he selects the set square and the protractor. He could also select nothing, or he could select everything. All of these selections he has made, they are all referred to as subsets. All of our selection here are sets of themselves, and they are all subsets of our original set of math equipment. Take note of a very important concept. If the set of everything is left out, that is, our set here of everything is left out, the other subsets are all called proper subsets. We're going to learn what a proper subset is as we go further in our class. Set A is called a proper subset of set B if every element of A is also an element of B, but there exists at least one element of B which is not an element of A. For example, if we have a set that has its elements 1, 2, 3, that set is a subset of another set that also has same elements 1, 2, and 3. This situation we could refer to be a subset, but it is not a proper subset. So if this is a set A and this is a set B, set A is a subset of B, but is not the proper subset of B. Let's take a look at another example here. If we have a set A with its elements 1, 2, and 3, and we have set B that has elements 1, 2, 3, and 4. A is considered to be a proper subset of B because A has all of its elements all present in B, and yet B has one element at least that is not present in A. We have a symbol to illustrate what a proper subset is. This is the symbol. So for our situation here, we say A is the proper subset of B. Let's go on. For example, if you were given set A that has elements 2, 3, 5, 6, 8, 11, 17, and 21, set B has elements 6, 11, 17, 5, 21, and 8, and set C has elements 8, 11, 6, 21, 2, 17, 3, and 5. Which of these is correct? Is A a superset of B, that is, does A contain B? Let's confirm if A indeed is a superset of B. If we compare the elements of our set A and B, we'll note that 6, which is an element of B, is also present in our set A. 11 is also present in both sets. 17 is present in both sets. 5 is present in both sets. 21 is present in both sets. And 8 is also present in both sets. So truly A contains B, because all the elements of our set B can be found in A. So we say A is the superset of B. Let's take a look at the other situation here. C is a proper subset of A. Is this a correct statement? Let's compare our set C again and our set A. If we took note, 8 here, which is an element of C, is also present in A. 11 is present in both sets. 6 present in both sets. 21 present in both sets. 2 present in both sets. 17 present in both sets. 3 present in both sets. And 5 is also present in our set A. In fact, if we did a careful comparison, we'll find out that all our elements in C are all present in B. So, set A and set C are equal. We can also say A is a subset of C. But A is not a proper subset of C. It's not a proper subset, but is a subset. So our statement here is what? Incorrect. Let's take a look at another example. If we have a universal set that has elements pineapple, banana, and guava, which of the following is correct? We have the set of guava is a proper subset of the universe. From what we've learned, indeed, the set of guava is a proper subset, because the set of guava can be found in our universal set that has guava in it, and it also has other elements that are not found in our set of guava. So this statement is obviously correct. Our second statement here that says guava is a proper subset of a universal set is a wrong one, because this statement without our curly brackets simply implies that guava is a set and not an element. We have explained that a subset is a set of its own that has all its elements present in another set. So this is not a set of its own, but an element. Therefore, our statement here is obviously wrong. Let's take some other examples. If we were asked to write down the subsets of the following sets, we have our first set here with elements 9, 10, and 11. If we began to list all the possible subsets we'll have within our sets here, we'll have the sets of 9. If we took them singly, the set of 10, the set of 11, and if we took them in twos, we'd have the sets of 9 and 10. We'd also have the sets of 9 and 11. We can have also the set of 10 and 11. If we took them in threes, of course we'd have the set of 9, 10, and 11. That is all of our elements listed. We could also have our empty set. So these are all the possible subsets of our set that has elements 9, 10, and 11. Let's take a look again at our second occasion here. If we have a universal set that has elements shirt, trouser, belt, and shoes, we would have singly the sets of shirt, the set of trouser, the set of belt, the set of shoe. If we took them in twos, we'd have sets of shirt and trouser, a set of shirt and belt, the set of shirt and shoe. We have the set of trouser and belt, trouser and shoe. We'll have the set of belt and shoe. We'll have the set of shirt, trouser, belt, shirt, trouser, shoe, shirt, belt, shoe, we also have the set of trouser, belt, and shoe. We also have the null set or empty set, and we have a set of everything, which is our universal set, which has shirt, trouser, belt, and shoe. All in all, we have 16 subsets of our universal set. Next, let's take another example. If B is the set of R, S, T, U, V, W, and X, which of the following is a subset of the set B? Let's do a quick comparison of our sets. We have the set F that has elements Y, Q, Z, P, G, and X. If we did a comparison of the set F and the set B, we would note that F is not a subset of B. Next, let's compare our set G. G has as its elements W, X, R, T, S, U, and V. If we did a comparison, we will note that W is an element which is present in B also. X is another element in our set G that is also present in set B. R is also present in set B. T is also present in set B. S is also present in set B. U is also present in set B. And V is also present in set B. All the elements of our set G is also present in B. We could say that G is equal to B, but G is also a subset of our given set B. Let's take a look at our set H also. We have set H with its element E, G, J, L, M, N, and P. We note that the elements in our set H cannot be found in the set B. They are disjoint sets. Therefore, H is not a subset of B. Only our set G was a subset of our set B. Let's go on. Quick facts for us to take note of. All sets are subsets of the universal set. So if you have a universal set, every other set under consideration is a subset of our universal set. The universal set, we said, contains all the elements in consideration under a particular problem. By definition also, all sets are subsets of themselves. By convention, it is agreed that the null set, which is also referred to as the empty set, is a subset of all sets. If we remember, in some of the examples we gave earlier, we had this situation in play. The null set was included as a subset of our given set in question. Also, another fact to take note of is that two sets are equal if they are subsets of each other. Finally, any given set S has two subsets. It has an empty set, which is a null set. We said by convention the null set is a subset of all sets. And by definition also, all sets are subsets of themselves. So the second set here is the set of itself, which is S. Let's go on. So far we've defined set as a collection of its elements. If S is a set, then the collection or the family of all subsets that we can have for that set S is what is referred to as the power set of S. The power set of S is denoted as P bracket S, where S is our given set. So if S is the set of elements A and B, then the power set of S is given by our set A, our set B, which are all subsets of our given set, our set AB, which is a subset of itself, and our empty set. This is the family or the collection of all the possible subsets of our given set, and again is denoted as P bracket S. Let's take a practical example to better understand our power set. Let's take a look at our example here. If we were asked to write down the power set of our set here given that has as its element pencil, eraser, and sharpener, let X be our set. The power set therefore would be what? P of X. And we'll have our power set as the family of all possible subsets that we can get from our given set. So first, if we took them singly, we would have pencil, eraser, sharpener, if we took them in twos, we would have pencil and eraser. We also have pencil and sharpener. We would also have eraser and sharpener. We would also have, like we learned, our empty sets or our null sets, and we'll have a set of itself, that is a set that contains all our given elements. And this is our power set. In total, we have 8 subsets in our power set. In summary, we've learnt about the different situations that arise as a result of interaction between sets. And one of such concepts we learnt about is the concept of equality. We said two sets are equal, that is A, for instance, is equal to B when all the elements present in A can also be found in B. Next, we learnt about the disjoint set. The disjoint set, we said, was more like an opposite of our concept of equality. In the disjoint set, our given sets have no elements at all in common. So our set A has its elements completely different from a given set B. Next, we learned about the concept of equivalence. We said equivalence is basically the cardinality or the count of two given sets that have equal numbers of elements. So our given set A has 5 elements, for instance, and our given set B also has 5 elements. We say that our set A and our set B are equivalent. Next, we learned about a very important concept of the subset. We said the subset is a concept whereby A, for instance, has its elements all found in another given set B. We also said B could have some of its elements not present in A, and that would give us a situation where A becomes a proper subset of the given set B. And lastly, we learnt about the power set. The power set being a collection or the family of all possible subsets that could be gotten from a given subset. With all that we've learned today, I'm sure you've become very conversant with the relationship that exists between sets. It has been a pleasure again for me taking you in my class, and I hope to see you some other time. Bye for now.